Hello, and welcome to episode 6 of the Sudokult discussion. And as always, I am David Rangsk Clamage, and with me is Philip Newman. Say hi, Philip.
Hi, Philip.
I knew you'd do that. See, Philip's the dad, so I can always trust him to make that joke. Speaking of, his kids are currently watching a movie, so we have until the movie ends to finish this episode. So
yeah, they're watching Cars 2. Very exciting.
Very exciting.
Very
Actually,
intense.
Yeah. All right, so today we are going to be going over the Oddagon. So no more set today, but it should still be very interesting. I actually really like this technique and would like to know more about it, so I'm interested in what Philip has to say. And with that, I think we should just let Philip get started. So go ahead, Philip.
All right. So we're going to start with this blank grid, just to talk about a few things. We're going to go back to alternating inference chains a little bit, just to review. So
yeah, and that we went over those in our first Sudoku episode. So if you want a primer on those, definitely watch that episode first, or try to muddle along with what Philip explains here.
Yeah.
But if you don't get it, go back and watch that episode.
I'm going to try and go over everything anyway, but yeah, you can check the first episode. So what we're going to say here is that 1 can't go in any of the gray cells in that row or in that column. Okay?
Right. So we're just imagining that 1 is limited.
We're just imagining. Yeah. So if you remember from the first episode, this is called a two-string kite. And the way it works is either there's a 1 here, or if there's not a 1 here, there must be a 1 here, which means there's not a 1 there, which means there has to be a 1 there. So either there's a 1 here, or there's a 1 here, or both. They could both be 1s.
Right.
We haven't said anything about this box, so we could have a 1 here, or something like that. Okay, so that's what a two-string kite is. And alternating inference chains in general, you have what's called a strong link, where you only have 2 possibilities, one of which must be true. They could both be true. In this case, only 1 can be true because they're in the same row. You can have a 1 here or a 1 here, but not both. But we have to have a 1 somewhere.
Right.
So it goes on one of those cells. So that's a strong link. And then a weak link, which is two candidates, 2 statements that can't both be true. So in this case, if we put a 1 here, we can't put a 1 here because they're in the same box. And vice versa. So we have strong link, weak link, strong link. So they alternate strong, weak, strong. And the result is a strong link between the ends of the chain. Which means, again, at least one of them must be true. Now that they're not in the same house, now that they're not in the same row or column or box, they could both be true. But at least one is true. Okay. So that's strong links and weak links and alternating inference chains.
Yeah, and from this, at least in this example, that means 1 can't be in row 9, column 9, because that cell sees both of the locations for 1.
Right. And we're going to come back to that cell in just a minute.
Okay.
All right. So the key thing with Oddagons, you might thinking through strong and weak links, well, strong links are strong for a reason. They must be better in some sense, right? So what happens if you just have a bunch of strong links in a row? And the answer is, it's usually not that useful. Except in the case of Oddagons. And the reason why it's useful is exactly what this kite tells us. One of these has to be 1, so that can't be 1. Alright, so let's think about this example. Let's say 1 now can't go in any of these cells. And that's a possibility. We already know that 1 can't go there. But
yeah.
Just for demonstration purposes. So we still have our strong link in row 1, and we still have our strong link in column 1, But now we have a strong link in box 1 as well between these two ones. And we also have a strong link here and a strong link here. So we have
just it's a circle of strong links, basically.
Circle of strong links. We have 5 strong links. That seems like it must be great. We've got 5 strong links. It's not great. It's impossible. You can never have an odd cycle of strong links. So that's why they're called oddagons, because it's an odd cycle. Okay. So let's just say, what if this is 1? Okay, this can't be 1, so this is 1. This can't be 1. Uh-oh.
Yep. Now we're to put 1 in row 9 now.
And you can kind of see why this can never work. Whenever you have alternating strong links like this, the ones have to be alternating in the cells.
Right.
You have to skip a cell each time. So you're always going to end up with the ends seeing each other.
Yeah, and since there's an odd number of strong links, if you skip cells, you're going to skip over...
You're going to skip a strong link somewhere. If you skip 2. So if you did that, that's fine here. We don't have our 1 there. But now there's nowhere to put 1 in the box.
Right.
Okay. All right. So how do we get around this? This doesn't seem very useful because it's impossible, so it could never actually occur in a puzzle. How we use it is avoiding it. So let's say, in this case, that could be a 1. So now what we can conclude, if this isn't a 1, we have an oddagon. And that's impossible. It can't happen. This is a false thing. So either we don't have a 1 here and we have an impossible thing, or we do have 1.
And since we're trusting that the puzzle we're trying to solve has a solution, we can just place that 1 there, because otherwise we would immediately encounter a situation where there's no solution. And this technique actually, maybe this will ring a bell for some people or help explain what we're talking about, is if you've ever done uniqueness patterns. And we haven't gone over uniqueness in Sudoku. We may not. But
we'll see.
We'll see. I'm not a big fan of uniqueness. So what uniqueness patterns are, just to really quickly go over them, we don't need to give an example or anything, is if a certain pattern happens, then the puzzle must have more than 1 solution. So I guess you could show that there. So those 2 3s there. If none of those 2 3s are given, then there's 2 orientation for those 2s and 3s that make a valid solution to the puzzle. Therefore, there's at least 2 solutions to this puzzle. So yeah, we can do 2s like that. We can do 2s like that. And there's nothing in the row, the column, or the boxes that will tell you which one's supposed to be 2 and which one's supposed to be 3, because there's a 2-3 pair in the row, 2-3 pair in the columns, 2-3 pair in the boxes. So yeah, now if we add a 4 there, then now we know that 4 must be true, or we must have multiple solutions. And the reason why I don't like uniqueness is that it assumes the sort of invisible 4th rule of Sudoku, which is if you're presented with a Sudoku puzzle, it has exactly 1 solution. And so if you're, say, setting a puzzle, you can't use that unless you've somehow used a computer to validate that there is only 1 solution. Because when you're constructing your solve path, until your solve path is complete and you've actually made a unique puzzle, the puzzle may not be unique, and then that uniqueness technique's not valid. And so the constructor very likely did not use uniqueness when constructing the puzzle, and so if you want to use their solve path, if you want to discover their solve path, then uniqueness is probably not part of it. Now, there are exceptions to that, and often constructors, if they do intend you to use uniqueness, will put in the rules as an additional rule, like something like a computer has validated there is only 1 solution to this puzzle, or something like that. But what's cool about the oddagon is we're not saying that if the oddagon exists, then there's multiple solutions. We're saying if the oddagon exists, then there's no solutions. So if you're planning on solving this puzzle at all, you better not form an oddagon.
Right.
So I like that a lot better.
Yeah. And it might seem that those are kind of similar things. Why can we assume that the puzzle does have a solution rather than no solution? Well, if it doesn't have a solution, and we're doing logic, even if it's assuming that it has a solution, eventually we're going to run into a contradiction and prove that it doesn't have a solution. Whereas with the uniqueness patterns, if we assume it has a unique solution and put a 4 there, well, it may be that it actually has 2 more solutions that look like that and like that. And we're just never going to find them. We'll find a solution with a 4, but we won't find any of the other solutions. We won't prove that it's unique.
Right.
But if we find a solution, assuming that it has a solution, we've proven that it has a solution. So
yeah, the logic is much tighter there.
Right.
Yeah, so if you've solved a Sudoku and you've used uniqueness during your solve, you've technically not actually proven that that is the only solution to the puzzle. And I think a lot of all other logical methods of solving a Sudoku, if you follow them and they're actually correctly implemented, then you've proven that the solution you've arrived at is the only solution.
Right. So going back to our kite, just as an example, I guess I can leave those. We know there's a 1 here or a 1 here, so there can't be a 1 here. We don't have to go and check, well, what if there is a 1 here? We know there can't be a 1 there, or either we need 2 1s in this row, or we need 2 1s in this column, or we need 2 1s in the box. One of those has to be true if there's a 1 here. And we've broken the rules of Sudoku. So we're no longer solving Sudoku. We're doing something else.
Yeah.
All right. So that's what an oddagon is. I've given an example where it is link 5. It's hard to make one link 3 because you can't really make a triangle using strong links unless they're all in the same house already.
Yeah.
And in that case, if you had something like this where one had to be in one of these 2, and one had to be in one of these 2, and one had to be in one of these 2, well, that's just obviously not going to work.
Yeah.
But I guess technically that is an oddagon, even though these aren't even strong links.
Yeah.
So
5 is our minimum.
5 is our minimum.
In a classic, I bet you could come up with some kind of variant to have a 3-link oddagon.
Possibly, yeah. So 5 is the minimum in a classic, but you can have bigger oddagons. So you could add to this. So say rather than having need a free cell, rather than having this column restricted, you could say, okay, these are restricted and these are restricted. And these are restricted. Lots more restrictions.
Yeah.
But now we have a 7-link oddagon. And you have the same conclusion. You have a bunch of strong links, except possibly this one. And since you can't have an odd chain of strong links, or an odd cycle, rather, of strong links, you have to break it by putting a 1 there. Okay. So that's what an oddagon is. This example is on a single digit. So all of these strong links are bilocal strong links. That means they're on a single digit in a house, right? As opposed to a bi-value strong link, where you have 2 possible candidates in a cell.
Yeah. And if you remember our first episode, you might remember there's a third way to form strong links that we explained in that episode, which is by doing an almost lock set. Which are the hardest to find.
An example, but
you can just do a 2-cell one, like that.
Like that. So there's a strong link here between 1 in this cell and 3 in this cell, because these can't both be 2. Yep. So either this is a 1 or this is a 3 or both, but there is a strong link between those candidates.
And this can get much larger than 2 cells.
Right. Now, you have to be careful using ALS strong links for oddagon logic.
Interesting. Okay.
I don't know that it even works. But the reason is usually you're either staying on a single digit and using bilocal links, or the example we'll see in a minute, you're using entirely by-value cells, but you're not mixing them. So if all you're using is local links and you change digits, well, now there's not really a problem in me putting a 1 here and a 2 here and then continuing on. Usually. You can restrict your ALS so that can't happen, but you've got to be careful with it. Okay. So I've never seen an example of it in a puzzle. I'm not saying it can't happen, but be very careful with what you're considering a strong link and how you're counting them. It would be very easy to skip over a by value in a cycle where you're switching candidates,
right?
And miscounting that. So,
well, let's take a look at a by value oddagon, and then maybe you can show us a case where someone might think it's an oddagon, but it's not. If you have that prepped at all.
I don't have that prepped. I might be able to come up with something.
Okay.
Yeah, and we are going to start with a by value oddagon. I have an example of a single value oddagon.
Okay.
Which these are also called broken wings. I don't know why they're called broken wings, honestly. I assume it has something to do with wings being. I don't know really. I don't want to pretend to understand where all of the names in Sudoku come from.
Right. Whoever first talked about it named it that. And,
right. You know. Wings are a type of alternating inference chain, so maybe it came from that. It's sort of a broken alternating inference chain, but it's not even that because they're all strong. So I do have an example of that. They are much harder to see. You would think it's just one digit. That'll be easy. But it's really hard to see. Like in this case, maybe you can see that it's limited in these cells. The problem is you have 3 cells here that could be 1, and most of the time you're not going to mark that.
Right.
Unless they're in the same row or something, and then it's breaking something else in the oddagon. So by-value oddagons are actually a lot easier to see. I'm actually going to talk about those, and then tri-value oddagons, which sounds just completely ridiculous, before coming back to the single value.
Okay.
So let's look at this one. This is Oddity. This is by Shye, and it was in the Sudokult Gospel pack. All 3 of these are in the pack. So if you haven't done the pack and you want to try these puzzles, pause and try them. But if not, we're going to talk about how to solve all of them. So
okay.
So I've gone ahead and done her basic stuff. There are some singles that you can fill in. A pair here. Pair. But you get to this point and there's not really a whole lot to do. There's probably some more pencil marking you could try and do. You're not going to get really far. So what stands out to you?
I see a lot of 1-2 pairs, and then we've got like a 1-2s involved in triples as well that look interesting to me.
So we've got 4 1-2 pairs and cells. So I'm going to highlight those just because. And we also have some 1-2 9s. There's also a 2-9 over here. It could be important. I'm going to tell you that it's not, but it could be important.
Could be, yeah.
So when you see something like this, and it's not immediately obvious how to make a chain or anything like that out of it, like just as a quick example,
it's tough to connect those 1-2s to each other even.
Yeah, let's say this was a 1-2 instead of this. So now we have this pattern.
Yeah.
This is going to result in what's called a remote pair.
Right.
So if this is a 1, this is a 2, this is a 1, this is a 2. So these are different.
Right. And a lot of people will use coloring to represent that.
You could do it with coloring. That's the other option. And again, these are different. So that's a sort of pattern that you could find. it's not useful here because I just kind of arbitrarily put it in, but it can be very powerful.
Right.
We don't have that in this case. So another thing you might look for is an oddagon. When you're looking for an oddagon, what you're going to try and do is connect them. So we have 4 green cells right now. There's one obvious cell that we can use to help connect, and that's going to be this one, because it's going to connect the 1-2 pair over here to the 1-2 pair up here.
So just like what you did, if we imagine that 9 didn't exist, then we have a remote pair.
Not in this case. Well, yeah, we would have a remote pair between these.
Yeah, we'd have 2 identical values
between these
at the ends of it. Yeah,
these would be the same.
Yeah.
Yeah. So yeah, if that's not a 9, then these are all the same.
Right.
And these are the same. Okay. Well, we're running out of things to try here. So how can we connect the ends?
Yeah.
Include those.
Pretend those aren't 9s also.
Well, so it's not that we're pretending that they're not 9s.
Okay.
If all of them weren't 9s, now we have a problem. Now we have an oddagon, right? So 7 cells. And now it's all strong links. The thing about pairs like this, naked pairs, is that you have strong links between the 1s here or the 2s here. You have strong links in the cells themselves.
So could you think about this as 2 overlapping oddagons, like 1 on 1s and 1 on 2s?
Yeah, you absolutely could. So this was an oddagon on 1s and an oddagon on 2s at the same time. There's a strong link between 1s here, and here, and here, and here, and here, and here, and
back
here.
to the start.
All the way back to the start.
And we counted 7 there.
And there's 7. So no matter where we start putting 1s, even ignoring the 2s, we're going to end up with a problem.
Yeah.
It's easier to see with the by value cells, in my opinion, because it's true on both, but also because the extra candidates are in those same cells.
Right.
So those 9s are in the same cycle, right? Whereas over here, this 1, it just doesn't seem related. It's related because we've shown that this can't be a strong link, so it has to be here. That's how it's related. But it's not as obvious why we care about this possibility. But here, it's contained in the same cells. It's the same 7 cells, regardless. All right. So what can we conclude?
One of those 3, at least, is a 9.
Right. So the 9s are called guardians.
Which I really like that name. I think it's
it's good.
It's a good name.
So what the guardians are doing is they are additional candidates that are preventing the impossible pattern. In this case, an oddagon. It could be some other impossible pattern. We're going to sort of look at that. But what we've shown is that if none of these are 9, then we have a pattern of 1s and 2s that's an odd cycle, and there's no way to fill it. You can look at it as, if I start alternating 1s, I break it. But you can also look at it as, okay, this is a 1, 2, 1, 2, 1, 2. Now what do I put here?
Yeah, no value for that cell.
I can't put 1 or 2. So either way, that is better for you to look at it. All right, so if one of those is 9, that can't be 9.
We get an elimination.
We get an elimination. And that elimination opens this puzzle up because now we've created another 1-2 pair here.
And so we've proven where at least one of the 9s goes.
Yeah. Yeah, and in fact, another one of the 9s here is true. because that's not 9.
Right.
But at the very least, we've shown that this is a 9, and you can see that puts a 2 there, and that resolves.
It resolves the whole. Yeah.
2, 1. There's our 9. There's our 2. So we just resolve the whole pattern. So it can be very powerful. But usually what it's doing, just in general, is there will be some candidates that are preventing the oddagon. And you know that at least one of those candidates has to be true. So any cell that sees all of those candidates, or any candidate that sees all of those candidates, you know, can't be true. They don't necessarily have to be on the same digit.
Right.
You could have something like this, where now the only guardians here are a 4 and a 9 in this cell. So I know there has to be a 4 and a 9 in that cell, and maybe that's a 1, 2, and now we've got a naked pair. Obviously, right. That's not 4.
Yeah.
But
we're
that's
hallucinating
another type
digits
of
at this point.
right. That's another type of elimination that you can have. Yeah, so that's a bi-value oddagon. It's not that hard to explain. The trick is finding it.
Right.
And so what I suggest for that is usually what you're going to have is some bi-value cells on the same 2 digits in multiple houses. So here you have a row and a column that has naked pairs in both. And then you're going to have some way of connecting them that involves the same 2 digits plus potentially some guardians. If you have guardians everywhere, if you have something like this, it's true that these can't all be 1s and 2s, and it's also true that they can't all be 1s and 9s, and they can't all be 2s and 9s. But you have so many guardians, you're not going to be able to make an elimination.
Right.
There's nothing that sees all of the 9s in this case. But since we have that 9 up in the corner, well, now we only have 3 guardians in these 3 cells, and they all see the same cell. Okay?
Yeah.
So that's a bi-value oddagon. There are some classic examples of this that involve just 5 that look more like this sort of thing. Just clear this. So rather than having 1s here, we could instead have 1, 2. Can't type 1, 2, 1, 2, 1, 2, 1, 2, 3. So this would be another example of a bi-value oddagon. We can't have 1, 2, 1, 2, 1, 2, 1, 2, 1, 2 all the way around. So instead, this has to be 3.
Right.
So that's a little different from this case where we had 3 possibilities and they all see the same thing. In this case, we only have 1 possibility, so it just has to be true. There has to be a 3 there. But same thing, we could have a 3 here and a 3 here. One of those has to be true, so there's no 3 in any of those cells.
Right.
These are the sorts of eliminations you can make with an oddagon.
You could also even just have, like, say, only a 3 available in the 2 corner cells, the top, bottom left and top right corner cells, and then you would know that the 3 was eliminated from row 1, column 1, for example.
Yeah, so you can eliminate that 3. Yep.
So I have a question that probably will come up, and probably the answer is what I think it is, but is there anything you can do if there's an even number of strong links? Like, does that prove anything, or is it just saying, okay, that's fine, you can't do anything with that?
All right, so there are some cases where you will have an even number of strong links, and we've looked at some before. What is that?
That is an XY cycle.
That's an XY cycle, or an XY ring, or a continuous nicely. When you're just looking at the pattern, what you have is a strong link here.
Mm-hmm.
It's bi-value. A weak link between the 2s here. These can't both be 2. A strong link between 2 and 3. A weak link between the 3s. a strong link between 3 and 4, a weak link between the 4s, a strong link between 1 and 4, a weak link between the 1s. So we made an alternating inference chain that formed a loop. So rather than going strong, weak, strong, weak, strong, and having strong on both ends, the two ends also see each other and connect back up in a loop. And what that gives us is, the way you like to put it, it turns all the weak links into a strong link.
Right.
And it turns all the strong links into weak links, although they already were in this case.
Yeah.
So in fact, we now have a strong link between 1s here. We have a strong link between 4s here. So we eliminate 4 from here, 1 from here, 2 from here, 3 from here. But the result, now that we've proven that, is we have a loop of 8 strong links.
True. Yeah, we do.
Strong link, 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 strong link.
Strong link has no meaning anymore, but
yeah. So it can happen. It's usually very powerful when you have a pattern like this, because you're eliminating candidates from so many cells. You're eliminating candidates from all of those cells. And you can have the opposite, where instead of bi-value cells, you have bi-local links. Say, these were the only 2 places where 2 could go, but you have a 9 here. And these were the only 2 places 3 could go, and 4 and 1. The result is you eliminate that 9. So yeah, that can happen. When you have an even cycle of strong links, you're going to have some sort of continuous nice loop.
Okay, and then so you just use the continuous nice loop elimination criteria, essentially.
So if you already have the strong links, you probably don't have any eliminations.
Right.
So in that sense, having a chain of strong links or a cycle of strong links is completely useless. But it will show up if you've formed your strong links through some other logic.
Gotcha. Okay.
Yeah. But the only way you can have all these strong links is if you already know that there can only be 1s in these 2 cells and not here. So there's nothing to eliminate anymore. You can only have the strong link if you've already eliminated all the other candidates from this cell. So there's nothing to eliminate. Yeah. All right.
So that's basically the answer I expected. If you just prove some even number of strong links on its own, that does nothing. But you probably did something along the way that helped.
In the process of getting those strong links, you made a bunch of eliminations. Yeah.
Okay.
You can have the same thing with like a swordfish, or even an X-wing is a continuous nice loop. If one can only go in those cells in the rows,
right?
Ooh, that's not the color I meant. Then we can eliminate 1 from these cells, and what that's effectively doing is making a strong link in the columns as well.
And I guess once you have your even number of strong links, that means there's only 2 states to the final solution. So as soon as you break that, you're going to get a bunch of filled ins. So if you remember where those are, you might be able to more quickly solve them.
Yeah, remembering where they are is important. Whenever you have a continuous nice loop like this, once you know what any of the digits are, you know what all of the digits are, basically.
Yeah.
If there's 1 here, there's 1 here. You don't have to track through all your links anymore. But it's not giving you anything new in the sense of eliminations or placements that you wouldn't be able to get anyway.
Right. I
put a 1 here, then I know there's not a 1 here, so I put a 4 here, and I put a 3 here, and I put a 2 here. We already get that just from basic Sudoku. So. Okay.
Sorry for the digression, but I figured someone would ask anyway.
No, that's a good question. So even cycles of strong links, common and totally useless. Odd cycles of strong links, impossible. Very useful if you almost have them.
Right.
So what an oddagon really is a almost impossible pattern.
Right.
And avoiding it. Okay. So let's talk about tri-value oddagons. These aren't really oddagons in the same sense. I call them tri-value oddagons because there's some similarities, and I don't really have a better name for them. These are a fairly new thing to be talking about. And I'll explain where these came from in a minute. But looking at this puzzle, the first thing that should be apparent is all of these boxes have 6 givens in them.
Yeah.
And they're all the same givens. So I can immediately just put in a bunch of candidates, right?
7, 8, 9.
In fact, that can't be 7 because there's a 7 here. But that doesn't really matter for the pattern.
That's highly suspicious, by the way.
highly, highly, highly suspicious. In fact, the 3s here are placing a 3 there. And so we almost have this pattern in this box. The only difference here, so all of these could be 7, 8, 9, but we need a 5 somewhere.
Right.
Okay. So this is what we're calling the tri-value oddagon pattern, or a tri-value oddagon pattern. This was sort of, it's not a new discovery exactly. So a while back, somebody had made a study of impossible patterns among 3 digits.
Okay.
Just go back to my sandbox real quick. Clear all this. So what they were looking at is if these 3 cells are the same digit, and these 3 cells are the same digit, and these 3 cells are the same digit, where can those 3 digits go in this box? And the answer is, well, they can go in some different ways. I think they can go like that, but there are some ways that they can't go. They cannot all go in those 3 cells.
Not immediately obvious to me why. But...
Right, not immediately obvious, and we'll get to why. I mean, this is literally just a morph of the puzzle.
Uh-huh.
But we'll get to why that is. And there are some other ones. I don't remember exactly how many valid configurations there are, but they had looked at this. What I hadn't seen, and maybe this was out there, is making actual eliminations based on this.
Right.
In a way that a human solver can do it. So when this came about, wrong puzzle. As I've talked about before, in addition to setting sometimes easy puzzles and sometimes impossibly hard puzzles and everything in between, I also generate puzzles, and I generate very hard puzzles.
Right.
And fairly recently, I have discovered the hardest puzzles for particular clue counts. So minimal puzzles that have a high number of givens. So say 30 givens. But they're minimal in the sense that if you remove any one of those givens, it's no longer unique.
Right.
This wasn't a very well explored area. For a long time, there was a 37 clue non-minimal puzzle that Sudoku Explainer rated 11.2, which is very hard. The highest known are 11.9. I think I've mentioned that before.
Right.
Something like an X-Wing is 3.2. Something like a Swordfish is 3.8.
Even a very complex AIC.
Your basic AICs are in the like 7.1, 7.2 range. So 11, we're talking about crazy dynamic chains with other chains in them. And
I think you said you found one where like you copied it all into like a Word doc and it was hundreds of pages long.
Yeah, so this is a very big digression.
Yeah.
In at least on the fork of Sudoku Explainer that I use, I was looking at one of the 11.9s, I think. maybe 11.8. And what it'll let you do is find all of the possible steps within a level of difficulty. And so have an 11.8 for a puzzle means that the hardest step that you actually need to use is an 11.8. But that doesn't mean there aren't harder steps available.
Mm-hmm.
So I scrolled all the way down, like hundreds of possible steps, because these are so complicated that there are gonna be a lot of different candidates that you can do that are even harder. This was like a 12.7. It was 330 pages or something like that when I pasted it in. It's just a stupidly complicated nesting of chains.
Right.
It's not the way a human solves a puzzle.
Right.
Now, some of the simpler dynamic chains, I could explain at least what the logic is. Maybe sometime we'll look at some of those just for fun.
Okay.
He says fun. Like, it's not.
It's fun for us.
Anyway, so yeah, for the higher clue counts, 11.2 was the hardest known for a long time, and I finally started finding some that were 11.3, 11.4. I've climbed all the way up to I have a 30 clue count. That's 11.6. Maybe a 31 clue. Anyway, so I was posting these on the forums, and somebody pointed out that basically all of the high clue count and minimal puzzles that were really, really hard had this same pattern.
Oh, interesting.
And it's not totally surprising that they would have the same pattern because of the way I'm generating the puzzles.
Mm-hmm.
I'm taking the hardest puzzle that I haven't used before, and I'm doing a neighborhood search on it. So I'm removing a clue and adding a clue, or removing a clue and adding 2 clues. So on. So 99 times out of 100, the resulting puzzle is going to have a very similar pattern. And if that is what's making it so hard, according to Sudoku Explainer, it's probably still going to be there. Or the given that I added just made the puzzle trivial.
Right.
That can happen. Sudoku Explainer is very chain-based. So it's starting from AICs and working your way up, but you're always using chains after that point. Not a lot of global patterns. It doesn't have any idea about set. It doesn't have any idea about exosets. And it doesn't have any idea about this. Even bi-value oddagons, it can't really do, unless they're very simple. So, what is this? We have a very suspicious pattern of 7, 8, 9. All of those cells are from 7, 8, 9.
Right.
We have 2 possible cells where there can be a 5 here. It turns out that one of these placements is impossible. So the other placement has to be true. And it turns out that the 5 has to go here.
Based on what you drew before, I could have predicted that.
Right. So this is the impossible pattern. If the 5 is not there, then all of these green cells have 7, 8, 9. Okay. It's not immediately obvious why this is true.
No, it's not.
Not even immediately obvious why this could possibly be related to an oddagon. Where are the strong links?
Yeah.
Okay, we have strong links here because we have a pair.
Now that 7 isn't actually necessary for the pattern, though, right?
Right. It's not necessary for the pattern. Even if this 7 weren't here, and these could be 7, this is still impossible.
Right. Okay.
So when I talk through the logic of this, I'm gonna totally ignore that 7. But yeah, if that 7 weren't there, we wouldn't have any strong links here, right?
Yeah.
We would just have a bunch of triples. Here we have a few strong links. There's a link between 7s here, 8, 9 pair there. But that's it. We're not making any sort of cycle out of those.
No.
So we have to kind of go one step further on this. So what I'm going to do is bring it up over here. And there are a lot of different patterns like this that you can prove are impossible. So it's just kind of, if you come across a suspicious pattern like this, and you don't immediately know which one is impossible, you're probably just going to have to check. So it's going to feel a little like bifurcation.
Yeah.
But I'm hopefully going to explain how you can avoid it feeling as much like bifurcation, where you're proving the pattern itself is impossible. You're not proving a particular placement is impossible.
I mean, it's almost like you can kind of think about almost every technique we use. We sort of memorize certain patterns that aren't impossible. Like you can reprove it every time, but by naming the technique and remembering the pattern of how to look at that technique, we've shortcutted having to reprove that. Even something as simple as the X-Wing, like we could reprove why an X-Wing proves all the eliminations that it does, but you can also just remember that if you get that X-Wing pattern, it causes those eliminations. So.
Yeah. All right, so what I'm going to do is going to feel exactly like bifurcation. I'm going to put a 7 right there.
Or even trifurcation.
Trifurcation, yeah. There you go. Why am I putting a 7 there? Well, it literally doesn't matter. That has to be something.
Yeah.
And we haven't picked anything yet.
Right, so basically when we do this, we don't have to try 8 and 9 there because it was arbitrary to try 7 anyway, and it's an identical.
Yeah, and in fact, I'm going to get rid of the pencil marks because they don't really even matter.
Okay.
Just remember that what these green cells mean is we're saying that those cells can only contain 7, 8, 9, or whatever 3 digits we care about.
Great.
All right. Now, there are a few possibilities. This is the part that's going to feel like bifurcation.
Right.
There are a few possibilities for where 7 can go in the other boxes. So let's start in the bottom right corners of these boxes. We have 7s here. Where does 7 go in box 1?
Middle cell.
Okay. Now, we have all of our 7s. So what do we have left? We have a bunch of 8, 9 pairs.
I'm counting strong links. 7. Okay.
That's 7, yeah. So what happened, effectively, is this cell got left out of our strong links. It's kind of related to these both being 7. I don't really have a good explanation of why this always happens, but for some patterns, it always happens, so they're impossible. So effectively what we've shown is that our arbitrary choice of 7 here, plus putting whatever that digit was into these cells, led to an oddagon on the other 2 digits.
Right.
That's an impossible pattern. Okay.
So we can't do that.
We can't do that. All right. What if these were in these cells? And note, by symmetry, this is exactly the same case as this.
Okay.
We can flip it over the diagonal and get the same thing. But I'll go through them both anyway. So now 7 can't go here and it can't go here. So it's going to go here.
So now there's another oddagon. Yeah.
Now there's another oddagon. And this time this cell is getting left out. Why is that cell getting left out? I don't know.
Maybe someone could do a more holistic analysis of this.
I think what it ultimately comes down to, and the same here. So we had a 7 here, here, and here before.
Yeah.
This cell sees 3 of those.
Right. Same as that one. Yeah.
Sees 3 of those. So I think that's kind of the underlying reason as to why that's the cell that gets left out. All right. So I said I would go through this one as well. Same thing is going to happen. That can be 7, that can be 7, so that's a 7.
So which cell sees 3 before we even... That cell sees 3. Okay. So that's going to be the left out one.
That's going to be the left out one.
And yep, that does it.
And just by nature of the conditions that we have. So the conditions were all of the green cells contain 7, 8, 9. We've already placed our 7s. So we have 8, 9 left. And one of the cells got left out. So we know there's going to be an odd cycle in the remaining cells. Because anywhere two cells see each other, we have strong links.
Right.
In this case, we have a naked pair of 8, 9. We have a naked pair of 8, 9.
And there's 7 cells.
And there are 7 cells in the cycle. So, yeah, for single values, you can think about strong links. For bi-values, you can think about the strong links on the individual digits, or you can think about the number of cells that are bi-value. So that works the same way. All right, last case. If they're in the center, it's a little different because both of these see this cell, right? So we could put a 7 here or here. It's going to turn out the same again by symmetry. 7 here, we could flip the whole puzzle over the diagonal, and it would move the 7 over here.
Right.
But we'll go through both cases. Now this cell sees 3, right?
Yep. So that's the one. How do we leave that one out? Okay.
This also sees 3. And this also sees 3.
Oh, I see.
We actually only have 5 in this one. But it's still an oddagon.
It is.
Yeah. But there's definitely something here with this particular pattern of green. No matter how we arrange whichever digit we're looking at, we always end up with an odd number of cells that see 3 of that digit. And they get left out of the cycle.
Okay.
So I haven't really rigorously gone through why this works. That might be an interesting thing to do at some point. But same thing here. Just moving over here. Those 3 get left out. Get the oddagon there. So yeah, basically there are 5 arrangements of 7, starting from a 7 being here. We had 7s there, we had 7s there, we had 7s there, and then we had 2 cases with 7s there. Obviously 7 can't go there or there because we put the 7 here. In all 5 of those cases, we ended up with an oddagon on the other 2 digits. So that's kind of the relationship to oddagons. It's not an oddagon in the sense of there being strong links per se. I guess you could kind of consider this like a tri-value strong link of some sort. I don't know. It's a stretch.
I think the terminology fails us at that point. But the way I'm thinking about it, just after hearing you describe it, is there's a bunch of oddagons hidden in that pattern.
Yeah.
And there is no way to avoid any of those oddagons. So there's a ton of oddagons in that pattern, and no matter what you do, you're going to hit at least one of them.
Yeah, that kind of makes it feel like unavoidable sets.
Yeah.
Which is a uniqueness thing. So relating back to uniqueness.
Yeah.
Since we talked about uniqueness, unavoidable sets are where you have a solution grid, and looking at the solution grid, you can see a uniqueness pattern. Say whatever this is a big diversion, but
that's fine.
Let's say
we have gray, and
let's say we have gray and green. Say our solution grid. So we're imagining this is entirely filled with digits.
Yeah.
But in particular, we have a 1, 2, and a 2, 1 there. For that solution grid, any puzzle that has this as a solution, in order to be unique, has to contain one of these at least as a given. Yep. Or we would have that deadly pattern that we talked about before.
And this is actually extremely useful to know as a setter. Because often you'll be setting a puzzle and you'll be like, it keeps coming down to these cells, and no matter what I do, I have multiple solutions. And if you actually take a step back and like look at what one of the final solution, like what all of the final solution grids look like, you'll see that it's just, this 1, 2, and 2, 1 are swapping
Yeah.
And so there's always going to be two solutions unless I do something to one of those 4 cells to distinguish it to not being a 1 or not being a 2. Just in this example.
And using David's solver with F puzzles makes this extremely easy to find.
Yep.
I see this all the time where I'm setting a puzzle and I'm trying to make it unique, and then all of a sudden I see green, 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 green on whatever digits.
Right.
Imagine those are green. And the solver is telling me if I make this a 5, it becomes unique. If I make this a 6, it becomes unique. But right now, there's 2 solutions because you have a deadly pattern.
Yeah, exactly.
So I see that a lot. Yeah.
Which means you got to put a given in one of them. And so sometimes if I discover that late in my solve and all of that ends up being, it ruins what I'm trying to do with my setting, I'll back up as much as I can to when it wasn't a deadly anymore, and I'll try to force the non-deadly candidate to be the true one in my solution.
Right. Yeah, I do the same thing. A lot of times what will happen is I'll be setting a variant. Say I'm setting a puzzle with, I don't know, fortress cells or something, and I end up with a deadly pattern that's in those fortress cells. Well, I don't want that because I'm trying to avoid putting a given in those cells.
Right.
So I'll backtrack just enough to where those cells now have some other candidate in them, and then I'll force that candidate into those cells without putting a given there.
Right.
And that's kind of how you can get around it. Okay, so that's a big diversion. So the point of all that is that this particular pattern of 3 digits is impossible. There are other patterns that are impossible. Ultimately, if you're finding this in a puzzle, unless you just happen to see exactly the same pattern, you're probably going to have to prove it. And the way to prove it is just to do what I did. Pick some places to put one of the digits.
Trifurcation.
It's trifurcation, yeah. So say those are all 7. What's the problem? Well, now I have an oddagon on 8, 9. And make sure that's true in every case. Because it could very well be, if we looked at this case, and said the 5 was here, well, maybe if we put 7, 7, 7, 7, we have an oddagon there, it's probably just fine. Yeah, that may just always work. There could be an oddagon in theory. In this case, there's not. That one's going to get left out, that one's going to get left out, and I think we're fine with a loop like that.
Yeah, if you leave out 2, then you're fine, right?
Yeah. But it's possible that some particular configuration of 7s could leave you with an oddagon on 8, 9. That hasn't proven it's impossible unless you've tried all the configurations. And in fact, we just found one that is not impossible. At least it's not immediately obvious when it's impossible.
Right.
Okay. So the conclusion of this then is if this pattern of greens is impossible, well then that can't be green. Because that is our lone guardian against this pattern.
So is this one of those puzzles that SE says is extraordinarily difficult? Or?
This one I think is like a 9 point something.
Which is, I think once you get into the 9s, unless you're
it's
really,
dynamic chains.
Yeah, you're going to have a lot of trouble without bifurcating, basically.
Yeah, I think if you put this in like the Sudoku wiki solver, it would probably get stuck. Yeah, I made this one by hand, but I mean, obviously I was starting from a point of having all of these givens. So there was only so much that I had to do after that.
Right.
But yeah, you can have this sort of pattern with the other givens in a different place that are less symmetrical and not designed to completely collapse the puzzle, Because once you put this 5 here, it's an easy puzzle.
So can we call this pattern Thor's hammer? Because that's kind of what I'm seeing.
Thor's hammer. Yeah.
You can't lift it, so it's impossible.
I kind of thought this looked like the on-off symbol.
Oh yeah,
like the power symbol just turned.
The 1-0.
Yeah.
I was thinking Pac-Man as well. He wants to eat those
Pac-Man.
dots.
Yeah. Of course, the good pattern here is like a weird sideways G.
It's like a G. Yeah, it's like a G for good.
G for good. But yeah. But yeah, there are puzzles with this pattern that are very, very hard. Unless you know the pattern. And then they're just very hard instead of very, very hard.
You still have to find the pattern.
Yeah.
And remember. Yeah.
Well, no, even after you have the pattern.
Oh,
okay.
I
set this one to be solvable after you fill in the 5
Gotcha.
here.
Okay.
That doesn't have to be the case. A lot of times with the very hardest puzzles, the same is true with exocets. A lot of times you'll do your exocet and the Sudoku explainer doesn't know anything about exocets. So what it thought was an 11.8 is now an 11.2. Congrats. Move down a level of complexity, but you're still not ever solving this.
Yeah.
But this is generally pretty powerful. In the examples that I've looked at, it's lowering from 11 point something to 9 point something in most cases.
Just still very significant.
Yeah, I haven't checked any of the really hard puzzles to see if any of them get lowered further. I will do that sometime. Mm-hmm. I'm curious. How are we doing on time? I feel like we went on a lot. It's been an hour. Yeah. All right, so we'll look at the last one really quick. I don't have any example puzzles. We linked last time to the big Sudokult pack.
We'll link to the pack again, and I'll point out which of these 3 that we covered. Yeah,
all 3 of these are in the pack. This one is by Shye. It's called Oddity. This one is called Trillium. But you will immediately see it in the pack because it has this crazy number of givens right here. This one's called Dragonfly, and it I kind of feel like it became infamous among the people that did the pack.
Because it's so hard.
A lot of people got stuck on it.
Yeah.
So this is one that I set trying to incorporate this particular pattern. It's just really hard to telegraph. So some techniques are really easy to telegraph. Look here. This one, you might guess where to look, but actually seeing the pattern rather than bifurcating is tough because it's just a complicated pattern. Where do you think we might want to look?
Ooh, putting me on the spot here. I don't know if you've
seen this puzzle.
I have not seen this puzzle, so I am blind. Okay, well, what I'm looking for is a cluster of like a lot of the same givens. Like box 1 has 3, 5, 6, 9. But I'm not seeing.
So this is the problem. This is why this is so hard to spot. So the digit you care about in this case is 1. And there's only 2 given ones.
Yeah.
You're thinking, how is 1 possibly restricted? Well, all the other givens are restricting it. But also, it's just not that restricted.
Mm-hmm.
But it's restricted in a way that makes it possible to make an elimination. So the rows and columns we're going to focus on are these. This is going to be kind of suspicious. It looks kind of Tatooine Sunset-ish as far as the givens, or as far as the rows and columns. Nothing to do with the Tatooine puzzles. But we're going to look at where 1 can go in those.
Okay.
And then the thing that might tip you off more than this is where can 1 go in this box?
2 places, yeah.
Can only go in these 2 places. When I see this sort of thing, where a digit is limited in 2 places on a box that aren't in the same row or column, if they're in the same row, I'm looking at pointing pairs and things like that. Mm-hmm. But if they're not, I'm starting to think, okay, is there a 2 string kite here? Is there some sort of AIC using this? Or is there an oddagon? Because this sort of pattern is very common to oddagons.
Yeah, it's one of the few ways to continue the loop.
Right.
You know.
If you're alternating between row, column, row, column, row, column, you're always going to end up with an even number of links.
Yeah.
You have to have a box somewhere. And you have to have an odd number of boxes, in fact. I think that's true.
Sounds right.
That may not be true. You could have an uneven number of columns and rows if you have boxes, I think. Anyway, I don't know. Maybe it's true. Puzzle for everybody. Determine if that's true or not.
Can you make an oddagon with 2 boxes? Go.
Yeah. All right. So this is a little suspicious to me. So I might look at where one can go in those rows and columns. Well, one is limited in row 5 because it can't go in any of those places. It could go here.
Yeah.
Column, same thing. Row 4 is kind of the same way. And you might look at wrong pencil marks. You could look at that too. Let's see. I said row 8, right?
Yeah.
We're going to have the same sort of limitation, 3 places. Column 8, same sort of limitation, 3 places. And keep in mind, these are column pencil marks.
Yeah.
Box pencil marks. That can be very confusing.
Tough, yeah. I mean, so I think if someone
probably just highlight at some point.
I don't know if everyone does the same, but if I'm looking for single-digit patterns, usually focusing on fish, I'll just highlight every single cell that can be like that digit. Like,
yeah.
Blindly, I'll just go through every single row column and I'll just highlight everything, and then I'll stare at what I've colored and hope to find something.
And this should be very symmetrical, so that should be all of them, I think.
Yeah.
That's all the places one can go. We'll get rid of our pencil marks. Make it easier. Add pencil marks to every cell. All right.
Yeah.
Well, there's nothing immediately jumping out. We don't even have. We have 1 strong link. We have that.
Well, box 9. Box 9.
Oh, box 9. We have 2 strong links, and they're both the same sort of pattern.
Mm-hmm.
It just doesn't seem like there's much there. Surprisingly, there is, though. So what I'm going to do is I'm going to start here, and I'm going to use row 5, and I'm going to color these, I don't know.
Blue is good.
And then I'm going to look at column 2. I'm going to add that. And then I'll go over here, go up here, and I'm just going to make a loop and see what happens.
Right, because in general, you're not going to find an oddagon. If you find an oddagon, your puzzle's broken.
Right.
So we're finding an almost oddagon, so we're just sort of pretending certain things don't exist.
Yeah, and in a lot of cases, this isn't going to tell you anything.
Right.
But one is sneakily limited. Because of where these are, it's clearing out all of this space.
Yeah. And the box.
And it's clearing out the boxes. Yeah. And that's a big chunk of space that's making it kind of limited. What it's doing in this case is this would be an oddagon. Mm-hmm. So if all of these were actually strong links, we would have a problem. They're not actually strong links. But the Guardians in this case, so in order to prevent this being a strong link, this could be a 1.
Yeah.
We don't know that it's a 1 because maybe this can be a strong link. Preventing this from being a strong link, we would need that to be a 1. Preventing this, we would need that to be a 1. We can't prevent this. This is a strong link. This one, and this one. Now we have 6 different cells, which may or may not be 1, but what we know is at least one of them is 1.
Right. And now, because it was something that I initially thought would happen, row 9, column 9 is not orange, even though it has a strong link with one of the blues. It's because that being a 1 doesn't actually guard any of the strong links we used.
Right. Yeah, if this is a 1, we can still have 1 here, 1 here, 1 here.
Yeah.
All it does is prevent this from being a 1, but preventing one cell in the loop is not enough to prevent the oddagon. The thing with loops is that you're skipping cells anyway. So it's just telling you have to skip this cell, but now I still have a problem.
Right. You have to prevent the strong link itself. Yeah.
The Guardians are preventing the strong link, and they're saying neither of these is a 1. So I don't even have a loop anymore.
Right.
Now I can put ones like this, or I could put ones like this. And there, and wherever else.
Yep.
So that's what the Guardians are doing. They are, in this case, preventing the bilocal strong links. Now, all of these are not 1, obviously. These can't both be 1.
Right.
So one of these rows actually does have a strong link on 1s in the blue.
Okay.
Maybe both of them. We don't know. But what we do know is that all of the blue links can't be strong links. There has to be at least one case where neither blue cell has a 1. In other words, at least one of the orange cells is a 1, and this cell is not.
It sees all of them.
It sees all of them. Yeah. And you can actually make this even more complicated, believe it or not. You can include these as blue, and include these as orange. You can include these now. That's orange, that's orange.
Wow.
You can just get silly. Somehow in this mess, if 1 is limited to blue cells, you're going to have an oddagon. This is very much akin to this sort of pattern.
Yeah.
Where this is just an impossible pattern for 1 being in only those cells in the rows and columns of boxes. Partly because of the way this is turned. Mm-hmm. This is a very common thing that you'll see with Two String Kites or Oddagons like this. Other cases, the tri-value cell, we were kind of making a circle, right?
Mm-hmm.
And then we messed it up by going this way instead. Well, here we're kind of making some sort of something.
Some sort of something.
Where these are like this, and you can kind of see they're sort of making a circle, and then this just messes everything up.
Yeah.
So no matter which cycle you pick here, you're going to find an odd cycle. You can do an odd cycle like this as another one. And then the Guardians to prevent those strong links. I don't remember which cells I picked. Something like that. Again. The Guardians all see row 1, column 1. That's how I set the puzzle. I set this up so that all of these Guardians are in row 1, column 1, or box 1.
So you wouldn't have had to find the exact one you pointed out, but there's a bunch hidden in there. There are multiple
options.
Yeah.
Yeah, you can just kind of start with whatever cell.
I guess starting with the box strong link is probably, like, maybe we could find one where we start with box 9 strong link instead of the box 5 strong link. I don't know if that's going to happen.
That's one.
Okay.
That may be a little hard to see because of all of the colors.
Yeah.
1, 2, 3, 4, 5, 6, 7, 8, 9. I used this box.
Yeah.
I used this box. I used lots of boxes.
I
guess I used 3 boxes. Anyway.
An odd number of boxes.
I used an odd number of boxes. So yeah, if we start here, we could go like this. Something like that. Using box 9.
Yeah.
Lots of different ways to do it. When I was initially setting it, I was going to try and make something that it was actually required to use all of the possible strong links. No, that's a terrible idea.
Oh my gosh.
But it does at least give you lots of options to find. So in this particular puzzle, it happens that was a 1-2 bi-value cell. So this
right.
becomes a 2. And that's what breaks the puzzle open.
So if you were going to bifurcate this puzzle, you might try one in row 1.
You try one there and you're going to have problems. But the thing with Oddagons, especially broken wing Oddagons, if I try and bifurcate this,
yeah.
So I eliminated all the ones from here. Mm-hmm. It's not immediately obvious that that's a problem. I have to bifurcate again, basically.
Yeah, you're going to have to keep
Can I put a 1 there? Okay, I have to put a 1 here and a 1 here. 1 here, 1 here. Okay, now I can't put 1.
Can you prove this is impossible by coloring at all?
Probably, yeah.
Because we've got a lot... every single box has 2 possibilities now. So I bet you could color... Ooh, you just got rid of all your colors.
I'm going to get rid of all my colors. I'm going to do that.
Yeah.
So yeah, let's say this is blue. So this is yellow or orange. That's blue. That's orange. That's orange. That's blue. That's blue. That's orange. That's blue. That's orange. And now this cell sees blue and orange. And
that cell sees blue and orange. So yeah, we've proven that this is impossible. So
yeah,
I think that's a good way to do it.
Yeah, and this is kind of what I was talking about, that this is in the wrong orientation.
Yeah.
If these were the cells that we had available, we don't have that problem. Now this can be blue and this can be orange, and we're fine.
Yeah.
But
now I'm wondering about going back to that the tri-value Oddagon, trying to color it.
Yeah, so originally the way I proved this was coloring.
Okay.
I don't know if it's easier or not. We can try it. So
probably want to get rid of that 5 there. Yeah.
I'm just going to color it.
Okay.
I know it's 5, but so what I did originally was say, okay, maybe this is red, this is blue, and this is purple.
Okay.
What can this cell be? Well, it could be red or purple. Let's make it red just for fun. Okay, this is blue now. This is purple now. We've got to make another choice over here. Let's say that's red. So this is
so it's
blue.
the same choices that we presented.
It's the same choices. But now what this is doing, purple is eliminated from these 2 cells. So it has to be here. But also blue is eliminated from those 2 cells, and it has to be there.
So it has to be both purple and blue at the same time.
Yeah, so same logic. Coloring will be simpler for some people to see, and actually filling in numbers will be simpler for some people to see. Either way, in this case, you have to go through a bunch of different cases. I would love to sit down and prove that a pattern is impossible without having to go through the cases, and maybe there's some sort of heuristic or some way to measure that this is going the wrong way, basically. but I don't know what that is right now.
Right.
But yeah. So this is called a broken wing, or a single value oddagon, or just an oddagon. A lot of people had trouble with this one. I don't blame them for having trouble in this one, because there's just so many possible guardians. It's not obvious at all that you should be looking for ones.
Even if you're told there is an oddagon,
even if you're told there's an oddagon on ones,
yeah,
it may not be obvious. Yeah. The thing with oddagons, though, is you really can just play around with picking a cycle that looks like it might be productive.
Mm-hmm. Just pick an oddagon that can't happen, and then look at the guardians.
Yeah, and then look at the guardians. And those all see the same cell.
Yeah.
We don't have to find all the oddagons. We just have to find one.
And then hope it's useful.
And hope it's useful, yeah. Yeah, it may not be useful. But in this case, all of them are useful because all the guardians see this stuff. So if you pick an oddagon on ones, you're in good shape. Pretty much. Alright, but yeah, that's all I have today. So 3 different, very, very different types of oddagons. But the underlying logic is kind of the same. You can look at it as a coloring problem where no matter how you try and color it, you're going to end up with a cell that can't be colored.
Mm-hmm.
You can do the by value the same way. Say blue, red, up.
Yeah.
But yeah, that's oddagons. Oddagons are a lot of fun.
Yeah, and so for people who like uniqueness, maybe this is another tool in your belt that's similar, but you don't have to depend on actually being unique. So
and you don't have to feel dirty after you use it.
Yeah, you don't have to feel like you got to take a shower afterwards because you didn't prove the puzzle was actually unique. Okay, I feel like people who use uniqueness are perfectly fine with it, but that's just a joke. Anyway, so thank you everyone for sticking with us through this episode. I know these episodes are long, but I hope you enjoyed it and maybe learned something. And if you do spot an oddagon in the wild, we'd love to hear about it. I get the feeling that it's a very much unexplored territory as of now, because I don't know of any solvers that actually look for oddagons right now, like the computer
YZF solver does.
It does. Okay.
Yeah, if you're looking for advanced techniques in a solver, YZF Sudoku is pretty much, well, it's not the only one, but it's one that is kind of on the cutting edge. It has exosets, it has MSLS, it has oddagons, it has ALS techniques. It has everything. But yeah, most solvers don't get to this point.
Yeah.
They stick with fish and short chains, and that's about it.
Yeah, if you're using Sudoku Wiki, it's not gonna tell you about oddagons. And unless Andrew Stewart decides to add it.
Well, so it actually does have a method called the pattern overlay method, and that may pick up on some oddagons. I haven't actually tried it. I'm curious about that. Okay. But the basic idea is looking at impossible patterns of givens. So in some cases, it should find them. But specifically oddagons, no, it doesn't have that implemented last I checked.
Alrighty. So thanks for everyone for sticking with us, like I said. And if you are not subscribed to the channel, please consider subscribing. I'm trying to get to 1,000 subscribers. That's the current goal. We're very close to 750 as of recording this, and so it's a pretty awesome milestone. I'm very happy about that. And I also have a Patreon with infos in the description for that. If you feel like supporting either the Sudokult episodes that I produce or the Learn to Love Sudoku, the simpler ones I produce. I also do 2 live streams every week. I also have my solver tools that a lot of people are using and enjoying. If you want to support any of that, my Patreon is a good way to do that monthly without having to remember to do that. You can also tune into my live streams, and you can donate through the live streams, or you can just watch and help me solve, and that's also awesome. And other than that, thank you, everybody. Check out the Sudokult pack in the description if you haven't checked that out already. I will point out which 3 puzzles are the ones in that pack that we covered today. and happy solving.
And just to set expectations, not that we've been super consistent about recording, but I am having surgery in about a week and a half, so there will probably be a break before the next episode, which is fine because we haven't decided what the next episode is going to be. So if you have any suggestions, let us know.
Yeah, definitely.
Interested in what you're interested in.
What do you want to know in the advanced Sudoku world? Have you heard of something you don't understand? Do you understand something that you think a lot of people would benefit from understanding? You can cover that. I know people have been asking whether we're going to be covering variants, so maybe we'll consider something along those lines as well, although up to this point, it has been just classic Sudoku. So with all that, thanks for watching, and
thanks, everyone.
We'll see you next time.